Introduction to Sound Waves 2. When the musician blows into the mouthpiece of the clarinet, it causes a thin wooden reed to vibrate. The vibration is transferred to the air inside the clarinet. This results in a stationary longitudinal sound wave being formed inside the clarinet. Click on the clarinet. When the musician blows across the mouthpiece of the flute, it causes a vibration in the air inside the flute. This results in a stationary longitudinal sound wave being formed inside the flute. Click on the flute. Sound is produced by stationary waves set up in a vibrating membrane such as in a drum. Click on the drum. In this lesson, you will be able to understand the formation of stationary waves in a closed pipe, understand the formation of stationary waves in an open pipe, understand the formation of standing waves in a vibrating membrane, and understand the formula for the frequency of sound waves produced in both open and closed pipes. Click play and observe the motion of air molecules in the pipe closed at one end where the longitudinal stationary wave is set up. The air in the clarinet can oscillate in several different overtones. For each overtone, click to highlight the air molecules at each node. What pattern of nodes and antinodes is common to all the overtones? Answer: each overtone has a node at the closed end and an antinode at the open end. What do you notice about the pitch or frequency of the sound of each overtone? Answer: the pitch of the sound gets higher for higher overtones. Frequency increases. Complete the above table showing the number of nodes and antinodes for the fundamental mode, first overtone, and the second overtone of the stationary wave in a closed pipe. The animation above shows the fundamental mode of vibration of the stationary wave set up in a closed pipe. Drag the slider to compare the full wavelength in orange with the length L of the pipe. What fraction of a full wavelength is equal to the length of the pipe? Answer: 1/4 of a wavelength. If the wavelength is lambda naught, then L equals lambda naught over 4, which implies lambda naught equals 4 times L. Hence, the frequency of the fundamental mode F naught equals V over lambda naught, which equals V over 4L. The animation above shows the first overtone of vibration of the stationary wave set up in a closed pipe. Drag the slider to compare the full wavelength in orange with the length L of the pipe. What fraction of a full wavelength is equal to the length of the pipe? Answer: 3/4 of a wavelength. If lambda 1 is the wavelength of the first overtone, then L equals 3 over 4 times lambda 1, which implies lambda 1 equals 4 over 3 times L. The frequency of the first overtone, F1, equals V over lambda 1, which equals 3V over 4L. What is the relationship between the frequencies of the first overtone with the frequency of the fundamental mode? Answer: F1 equals 3 F0. The animation above shows the second overtone of vibration of the stationary wave set up in a closed pipe. Drag the slider to compare the full wavelength in orange with the length L of the pipe. What fraction of a full wavelength is equal to the length of the pipe? Answer: the length of the pipe equal to 1 1/4 wavelength. If the wavelength is lambda2, then L equals 5/4 times lambda2, which implies lambda2 equals 4/5 times L. The frequency of the second overtone, F2, equals V over lambda2, which equals 5V over 4L. What is the relationship between the frequency of the second overtone with the fundamental frequency? Answer: F2 equals 5 F0. Air molecules at the opened end of a closed pipe are free to vibrate. The vibration extends outside the pipe by a small distance c. The antinode is not exactly at the open end, but at a distance c from the open end. The distance c is known as the end correction. The end correction c depends on the diameter of the pipe and the wavelength of the sound. Since the closed pipe has one open end, it has only one end correction. The relationship between the length of the pipe and the wavelength becomes as shown. For the fundamental mode, L plus C equals lambda naught over 4. For the first overtone, L plus C equals 3/4 times lambda 1. For the second overtone, L plus C equals 5/4 times lambda 2. Rearrange by dragging the boxes so that frequency, wavelength, number of antinodes, nodes and diagrams corresponds to each of the modes of vibration in the closed pipe. Summary: a closed pipe is closed at one end and opened at other end. For the stationary waves formed in a closed pipe, node is formed at the closed end. For the fundamental mode of vibration, the wavelength of the stationary wave is 4 times the length of the pipe. The fundamental frequency, F0, equals V over 4L, where V is the speed of the sound in air and L is the length of the pipe. If C is the end correction, for the fundamental mode, L plus C equals lambda naught over 4. For the first overtone, L plus C equals 3 lambda 1 over 4. For the second overtone, L plus C equals 5 lambda 2 over 4.